Welcome to this lecture on VHDL and the course Digital System Design with PLDs and FPGAs. The last lecture we have seen the VHDL coding of sequential elements along with the combination circuit. Then we have looked at we started on how to write packages, at least we did a preliminary kind of work towards it. So we will quickly run through the slides and get on to today's part. So the last class we have seen about the VHDL coding of synchronous reset in flip-flop. Unlike asynchronous reset, the synchronous reset is kind of synchronous with the clock. If it is active, then on the next clock the Q will become 0, and that is once the clock comes it has priority over the D. If it is active, then irrespective of the D this becomes 0. Then if it is not active, whatever on the next clock edge the D goes to Q. So naturally in asynchronous reset we have put it before this clock event clock is equal to 1. So that cannot be done. So this is synchronous to the clock. So everything happens with respect to the clock. So this reset in the sensitivity list is not required. Also we write the reset within this clock event clock is equal to 1 because it is synchronous, and we give priority to reset. So we write the reset first, then the Q comes second. So that is what is shown here, process clock. In this we write if reset is 1 Q is 0 else Q gets D, and this shows a kind of multiplexer structure with reset as a select line. When it is 1 Q is getting 0, otherwise Q is getting D. So the synthesize tool will put that multiplexer, we will see that, and we have also said that in a process the nestings allows us to kind of behaviorally represent the synchronous reset, but in a concurrent statement it is difficult, so it does not make sense. Once again maybe the synthesis tool will support some kind of syntax which at least kind of semantically does not sound correct. Yes, if it supports you can use it, but then I suggest that as far as the flip flops and registers are concerned you go for a process in VHDL, and this is what the synthesis tool make out of that code. The clock goes here. Now when reset is a select line of a 2 to 1 mux, when reset is 1 0 goes here, and reset is 0 then the D goes here, then you get what you want. We have looked at this, Q gets D and R gets Q. Definitely Q and R will get 2 flip flops, that is evident because you have an event on the clock. What is the current value of D goes to Q at plus delta time, current value of Q goes to R plus delta time. So you get something like this, which if you use a variable you will not get it. Now that you should know that the variable you could write this with a variable, and we will see that, but if you do an immediate assignment you won't get this. If you say Q colon equal to D, R colon equal to Q, then you will just get one R, one flip flop, not 2 flip flops, okay. And we looked at a shift register, how to model a shift register. So here it is an 8-bit shift register, we have made it a little awkward. D0 goes to Q0, Q0 to Q1 and so on, and you could write a loop within that clock event clock is equal to 1, that is one way, or you can view it as a kind of vector, that is Q7 down to 0 or Q gets Q6 down to 0 and concatenated with D0. So both, like this is the loop upon the clock Q0 get D0, and for I in 0 to 6 loop Qi plus 1 is Qi. That means for the 0th index you get Q1 gets Q0, for the 6th index you get Q7 get Q0n. But you could write like this, Q which is nothing but 7 down to 0 is Q6 down to 0 and D0, in one shot you get it, and that is also like I said, you could show as a single flip flop with thick lines, and the output is Q and the input is Q6 down to 0 and D of 0. So that is 2 ways of looking at it. I would prefer this any day than this. This also kind of at least for people who are not thorough with the syntax, it looks as if it is some loop is written, something which is consecutively executing, which is true for simulator, not for synthesis. And we have seen a counter, and this is standard logic unsigned is used, so that we are using a plus here, and clock reset is the input, 8-bit count output is the count is an output, and since we can't say count gets count plus 1, we define a signal of the same bit Q, which is of 8-bit vector, and in the code we will, in the statement region, we say count gets Q and write the code in terms of the Q. If reset is 1, Q gets other 0, otherwise upon the clock Q gets Q plus 1. So, and as I said, this plus, and one side is a standard logic vector, other side is integer. So this operator which is normally used for integer is overloaded in this particular package, that's why we use this package. So in this code, to notice the use of this particular package and the way we use signal to overcome the limitation of the output type of port, because you define something as output, then it cannot come on the the right hand side of an assignment, because then it is treated as an input. But if you declare a signal, it has no limitation, so that is kind of we overcome by this method, and this is something which you should keep in mind. And this is how it is synthesized, which say that upon the clock Q gets Q plus 1, so upon the clock Q will get Q plus 1, and that is how it is synthesized. And we have gone one level up, we have added an 8-bit input and a load signal. Again we treat it as a synchronous load. When the load is high, this DIN is loaded to the output, and when load goes low, it starts count from there. It is a synchronous load, so naturally this comes in the clock tick event and clock is equal to 1, and we give priority to that over the counting. And this is a signal declaration, standard logic unsigned library, and here the count is assigned with Q. Process clock reset, if reset is 1, Q is initialized to 0 upon the clock. Now this is the game, if load is 1 then Q gets D in, else Q get Q plus 1, end if, and this is the end if for the clock event, end process and end architecture. And once again this shows if load is 1 Q gets something, else Q get Q plus 1. So this shows a 2 to 1 mux where load is a select line, when it is 1 Q get the D in, when it is 0 gets Q plus 1, so that is shown here. So to the D, because everything is synchronous, the moment you write something underneath, then that is synchronous which is connected to D, and this represents a mux. When load is 1 Q gets D in, that is this, and load is 0 Q gets Q plus 1, that is how it is synthesized. And synthesis tool might optimize it further depending on the target, like in FPGA you may have kind of dedicated resources for this plus 1 and so on, so that could be kind of, and this could be a part of the logic resource within FPGA. You may not use kind of standard resources within FPGA, that is what I mean, and when we get to the FPGA we will understand it better. And this is a coding scenario. Topmost code will be normally in a complex case will be the structural code made of components, and each of the component could be further structural code depending on the complexity. But when it comes to the last level, normally level 2, level 3, this particular component, when it is reduced to a reasonable level, will be composed of some concurrent statement processes, procedures and things like that. That is how the coding goes, and the topic we have started was this, how to put a component in a package and put that in a library. Okay, that is what we have seen. The example we have taken was a flip flop, and the top level entity which used this as a component is a double stage synchronizer or a 2-stage shift register, whatever you would like to call. So its structure is very simple. The clock is called S clock, which is connected together. Input goes to the D of the first flip flop. The Q is internal signal which is connected to the D of the second flip flop, and the second flip flop output is the SOP. So we have seen how normally we write it. The library, the package, entity, D and clock are the input, Q is the output, and this is the behavioral code. The process clock, begin if clock event, clock is equal to 1, Q gets D, end if end process and so on. Now we are going to look at the code, this particular code. So we have the library, entity, these are the input, S clock is the input, SOP is the output. So as here input, S clock is the input, SOP is the output. We need a component called data flip flop, we need an internal signal. Okay. So that is declared here in the architecture declaration region. We have the component declaration with the D, clock and Q. We have a signal declaration and the begin. In the statement region we have instantiated this data flip flop twice with input S clock and internal one, then that is connected to the next input S clock and SOP. The game is over. Now what we are going to do is we are going to write, here we have assumed that this particular thing, the component and the top level code is in one file or in one project, but we are now what we are going to do is that we are going to write this in a package and put it in a library, and then we are going to use that library and package to do this kind of instantiation. Okay. So one thing, when we put something in a package, this part, the component declaration, will go along with the package than in the top level entity. Okay. You would have seen that in a, when you write a library, functions in a library. In C code you have a function prototype which is specified, which goes in the header file. Okay. So then you say hash include the header file, and then that comes at the beginning of the code, then all the data type is verified. Something similar happens here. Okay. We move this component along with the package and we are going to say use that package, and automatically that comes there and the compiler can check the data type when you instantiate. That is a game. So let us look at the how to write the package. We are going to write this component in a package and put it into a library. And so before that, a few word about the library and packages. The hierarchy of library is like this. You could have multiple libraries, and each library can have multiple packages, and each packages can have within it components, functions, procedures and data types. All these can be in a package. Okay. And there can be multiple packages. And mind you, there are predefined libraries, that means we are going to not to declare that, that is called std library and work library. Std library is a library which contains all the basic declarations and definitions of the VHDL. That means it contains the packages which declare the bit, the boolean, the bit vector, the operators like plus, minus, relational operators, logical operators with regard to bit and boolean. All that is in a package called standard, and that standard package is in the standard library. And the work library is when you compile something, when you work on a design you have written some entity and architecture and you are trying to synthesize it, simulate it. So during that process that entity and architecture is kind of compiled into this particular library, work library, and there are two packages in this standard library. One is called standard, and which contains all the standard data types, operators, functions and all that, and it also has another package called text.io, which basically has the all file declarations which can be used for test bench and writing something to the screen and things like that. And now mind you, these things are implicitly declared. You do not have to declare it when you write a code. You do not have to say library std comma work, which is already understood, which is implicit. You do not have to say. Similarly, you do not have to say use std.standard.all because that is also implicit. But what is not implicit is this text.io package. So if you want to use text.io package you have to use, like you have to say use std.textio.all. Okay. So that is a brief about the various libraries and packages, standard libraries, standard packages, what is implicitly declared, what is not implicitly declared and so on. And let us now see how we can write a counter, sorry not the counter, the D flip flop in a package. So this is how it is written. This is the entity and the architecture of the D flip flop. So you say library declaration, package declaration, entity which we call now DFF, the port is D and clock is the input, Q is the output, and we write the architecture declaration region with the process for the D flip flop. Now on top of that we write a package body which say the package some name is and that name, and within that you have to write the component declaration which was earlier in the architecture declaration region of the top level entity wherever you have used this particular component, but that is brought in here now. And suppose you have multiple components, then you can write within this package body the component DFF, n component, then component counter, n counter and so on, and then you have to follow it up with all the entities. Like if you have a DFF and a counter as component, then you put a library declaration, entity for DFF, architecture for DFF, followed with library declaration for counter, entity for counter, architecture for counter and so on. Okay. Once you do this, the package coding is over. Now this particular package has to be compiled into a particular library. Okay. Now this is the syntax for writing the package, but how to compile this package into a particular library depends on the tool you are working with. Okay. So you have to it depends, sometimes you work with some simulator like Model Sim, sometimes you work with a vendor tool like the Xilinx ICE or ISC or Xilinx Vivado or Altera Quartus tool and so on. Okay. So how to compile a particular package into a library is tool or vendor specific. Many a times it means that you have to specify a particular library and invoke the compiler with that particular library as a target. Okay. So if it's you are working with the command line, then many a times you give the compiler the command, the file name and some option as to which library it should go to. But in a kind of something with a GUI, you may have to choose particular library and compile or create a project which is specific to a library and compile this file in the project to a particular library and so on. But I am not able to say anything at this moment. Maybe when I give a tool demo I will show you whichever tool I am using, how that is to be done in a particular tool, but the essence is that you write the package and compile that into a library. For the time being, assume that this particular D flip flop, is in the package, is XY package, and let us assume we have compiled this package, this whole thing, into a library called xylib, okay, xy_lib. Okay, now we will see how to use that, okay, in the top level component. This is our top level component. So we write, now we have put this flip flop in a package called xy package and we have put it in a library. So we are going to say library xylib IEEE, use IEEE standard logic 1164.all, and we say use xylib.xypackage.all, because that is where this particular component is. And now this is the entity of the double synchronizer with input and S clock as input and SOP as output. Now as I said, since we say use xylib xypackage.all and the component declaration is part of the xy package, we don't have to declare the component, okay. That is already there in this particular package, and we declare the signal, internal signal, which is signal int1 is standard logic, and you just instantiate the component DFF. This is the first one, port map, D input goes to D, clock S clock goes to clock, and int1 is the output. Similarly the second flip flop, int1 is the input, S clock is the clock, and SOP is the output. The game is done. So that is simple. So the moment you put that in a component, that component in a package and in a library, not only you can use it, anybody can use this particular package and the library particular component, and they have to just say use xylib.xypackage.all, and they can use all the components within that particular package. So that's the meaning of this. That is how you write a package. Now when you instantiate, the same rule apply. We have seen the component instantiation. We have done a positional association. Formal to actual is associated positionally, but you could say you can say here the D can be assigned with the formal to actual, the clock can be assigned in particular order, in any order, like you can say clock is kind of associated with S clock, D is associated with INP, Q is associated with int1 as far as the first component is concerned. So that is how the instantiation is done. So now let us look at the little more detail when we write a particular component in a package. Say when you write the code for a counter, suppose you have written the counter as a 8-bit counter, okay, but somebody might need a 16-bit counter, okay. So or somebody might need a 20-bit or a 32-bit. Even if you think of present microprocessor or microcontroller scenario, you might end up with an 8-bit counter, 16-bit counter, 32-bit counter, and so on. So it is very awkward to write various size of counters and put it in the library. But if you look at the counter code we have written, everything is kind of like if you have an 8-bit counter, to go to 16-bit counter there is no much change is required. Wherever you have set the counter size, the output is say count is standard logic vector, say 7 down to 0. If you say 15 down to 0, automatically that becomes a 16-bit counter. That shows that instead of kind of hard coding the width, if we can specify it as a constant, and somehow, okay, we don't specify the constant value then, but when we instantiate, if we can specify what is the width we require, then we will get a generic counter whose size or which size is configurable, okay. Its size can be configurable, that is a basic idea. and that depends. In the case of counter it is very simple. It may not be very simple to write generic components with various parameters kind of configurable. You take a FIFO, you can have a configurable width, maybe FIFO has a width of 8 bit or a 16 bit, and you can also think of a FIFO with a configurable depth, like you can say a 256 Henry FIFO or a 1K Henry FIFO and so on. So maybe it is worthwhile to write a configurable width and configurable depth FIFO. And similarly you can think about it, say you think about a dual port RAM or a multi-port RAM where the width is configurable, the depth is configurable, number of ports are configurable, all that. And when it comes to that, it may not be that easy to write a generic kind of code, but at least in very simple cases it is very nice if we can write generic component which are configurable, which has configurable sizes, depth and so on. Okay, it is up to your need and imagination that you can write the generic components. So let us look at an example of a generic counter, okay, counter which can be configured upon the instantiation, that is our idea. So let us look at the slide. So this is how the generic, so I will show the code first, then I will show the package before that. So assume that we have a package declaration followed with a counter declaration. So the counter, you see the library, the packages, standard logic 1164 and standard logic unsigned, because we know that we are going to use q gets q plus 1. Here is the game. In the entity, when we declare the port, say the inputs are clock and reset, which is kind of in type, count is the output now which says standard logic vector. Now instead of saying that 7 down to 0, we define a constant called size, okay. We say size minus 1 down to 0, okay. If it is 8, then it is 8 minus 1 down to 0. If it is 16, then it is 15 down to 0 and so on, okay. Now we define a constant, and this is nothing but a constant. Generic is a constant, but the name given in this generic structure is this keyword generic, and we open the bracket and we give the name for that particular generic, size, its data type, okay, size colon data type, and its default value. This is not the fixed value. Suppose at the time of instantiation, if you don't specify any width, then it is taken as a 4 bit counter, that is the meaning of this, colon equal to 4. Now we need a Q signal in the architecture declaration region. The same thing applies. We say instead of particular width, we say Q is standard logic vector size minus 1 down to 0. Count gets Q, the code is same, clock reset, if reset is 1, Q is 0, otherwise on the clock Q gets Q plus 1 end if end process, okay. That is the code for a generic counter. Since we are putting this into a package, then we write a component package header with the library and the package, the 1164 package use close. Then we say package xy packages, then whatever was in the entity like the generic and the port, we write here generic, and which is same as the port declaration, whatever was in the entity declaration, then the port declaration, say n component, okay. Generic is required because you see that this data type need to be verified when we specify, when we instantiate, the compiler has to verify that it is integer, that is why it is written here. And now when you use, there are two ways of using it. When you exactly instantiate that in a top level component, the default value is 4. So you can say like earlier you can say C1 count port map, the clock, that means the clock goes to the clock pin, the reset goes to reset pin, and the CO goes to the output of the counter. Okay. So here you will get a counter with a default value which is 4 bit. Now suppose you want this to be an 8 bit counter, like port is mapped from formal to actual, we do a generic map. Formal was the constant size and the size is mapped to 8. So a label count generic map 8 and port map clock reset the CO. Mind you, in the generic you can have any number of parameters. Say you can think of a generic with size integer equal to 4 and then you have semicolon, then you say width colon integer equal to some default value and so on. So any number of generic parameters are possible, and when you map it you can say generic map, then the size is mapped to something, width is mapped to something, with a named association you can say that. So that is shown as an example here. Say we are writing this only for simulation, entity NAND2, that is the entity's name, and this is a port declaration. I1 and I2 is input, O1 is output of standard logic type, and we have two generic TPLH, that is a propagation delay, is of type time, default value is 3 nanosecond, TPLH type time 2 nanosecond, and somewhere in the code we are going to write O1 is I1 NAND I2 after TPLH plus TPHL divided by 2, because this is given, normally we say after 10 nanosecond, after 5 nanosecond. So now this is given a proper average of the propagation delay. So that is how the that shows another example of using the generic, which shows that the multiple generic can be used, more than one can be used. You have to map it definitely. When you instantiate you have to say NAND2 generic map, you can say maybe 5 nanosecond comma 7 nanosecond and port map and things like that. So exactly like this you can say. So that is how you instantiate a generic component. Now when you have generic in a hierarchy, okay, suppose we have a timer which is a generic timer. Suppose somebody has written a timer which is generic, and the width of the timer is specified as a generic called T width, okay, timer width. That means you write the entity timer here, you say generic T width is some integer and some width, okay, and we assume that after all the timer is nothing but a counter with some decoding. So we assume that in the timer code this particular counter is instantiated, okay, and counter itself is generic. You assume that the timer is generic and the counter is generic. So when you instantiate the counter in the timer, generic timer, the size of the counter, like we had a size generic, that can be, because if you write that to a specific value then there is an issue, because if the timer is going to be used instantiated by somebody else with a particular width, so naturally that has to come down to the counter. So you can say like say count generic map T width, which is nothing but the generic of the timer which instantiate this counter. So essentially the generic can be kind of hierarchically passed down through the components. That's meaning of it. I hope that is, I have made it clear, because to show an example I have to write so many code. So that's why this is, with this much discussion I think it is most probably it is clear in your mind. So that is about basically the libraries and the packages. We have seen how to put a component in a package. So there is a particular package body which has to come on top of the entity and architecture, and then you have to compile that into a particular library which is tool specific. And once you compile then you just say use that particular library dot the particular package dot all, and you don't have to say component, you don't have to do the component declaration in the architecture declaration region because that's part of the package now, and then you can instantiate the components. Then we have seen how to write generic components with a kind of generic width, generic depth and so on, so that when you instantiate you can specify the width or the depth or the sizes, so that you don't kind of write various size components for the library. You have a single generic component which when you instantiate you specify the configurable parameters, then you get what you want. And also we have seen that when you use it hierarchically, a generic component is used in a generic top level entity. The generic of the top level entity can be passed down as generic of the instantiated component. So that is a lot of jugglery with the words, but I think you can kind of catch the basic idea behind it. So let us move on. So that kind of completes the packages, but then there is one thing like when you suppose you have put a particular say counter. So you have called your particular counter a counter and you have put it in a particular library. Okay. Now there could be somebody else who might write a component called counter again and put it in some library, and you say at the beginning of the code library IEEE xylib mylib and so on, and then you say use xylib.xypackage.all, use mylib.mypackage.all. Assume that there is a component called counter in mylib and xylib, and somewhere you instantiate that particular counter, and depending on which package is kind of specified at the beginning, that will come from that. It may not be the counter that you want. Okay. So there has to be some way of telling the tool or the compiler saying that for this particular instantiation this particular component has to come from a particular library, particular package, and you can even maybe go very specific that maybe that particular component has multiple architectures. You can say I want this particular component and a particular architecture. So the way to specify that is called configuration, and there are two kind of configuration specification and configuration declaration. Okay. So the configuration specification basically is specified in the architecture declaration region, and it binds the component instantiated in the architecture statement region to a particular library. That means basically when you say configuration specification, we are going to instantiate a lot of components in the architecture kind of statement region, and those components can be declared in the architecture declaration region. But in the declaration region again we are going to say which library, which package, which is the entity architecture pair in that particular package to be used for this particular instantiation. That is what is configuration specification. But when you say configuration declaration, it is more than that. It is a separate unit, design unit. That means you write a entity, you write an architecture, and you write a configuration for that particular entity. Okay. It is a separate design unit and it is hierarchical. That means that you may write an entity and architecture with a configuration, and a higher level entity might use this particular entity architecture pair along with the configuration, and that top level entity can have its own configuration and so on. Okay. So this configuration declaration is a separate unit, it is hierarchical, it is specified at the end, you know. So you have, suppose you have a library and package, you have an entity, that entity might have multiple architectures, say architecture 1, architecture 2. At the end we specify the configuration which say at least which of the architecture to be used when we particularly kind of use that in a design, okay. That is a basic idea of configuration. So it does two things, it will bind the top level entity to one of the many architecture it has. So this configuration is going to specify which of the architecture is bind to this particular entity, okay. Also not only that, it will say that suppose this entity uses lot of components, it will say where those components, from which library, which package, which architecture it should be used, you know, which library, where it comes from, it specifies. So it specify the configuration declaration specify two things, it specify which architecture to be used by the top level entity, which are the components, where does the components instantiated comes from is specified. So we will see both, okay, configuration specification and configuration declaration. We take this as an example, the full adder. So equations are simple, A XOR B XOR C, that is the sum. So we are going to instantiate two components, two XOR gate, AB gives S1, S1 and Cin gives the sum, and so here it is the carry out AB BC AC, AB gives S2, BC gives S3, AC gives S4, then S2 S3 give S5, S5 and S4 gives C out. So 2 XOR gate, 3 AND gate and 2 OR gates, okay. So let us look at the configuration specification first. So this is the library declaration, we are say assuming that there are in addition to IEEE there are some HSLib, CMLib where these AND gates and OR gates and XOR gates are put, and this is the full adder entity. So ABC is the input, sum and Cout is the output, and this is the declaration region, and where we declare the components XOR 2, D1 D2 is input, DZ is the output, and 2 we specify the output first then the input in the AND 2 component, and then the OR 2 component where the inputs are first then the output is the second, and we declare the internal signal like S1, S2, S3, S4, S5. So S1, S2, S3, S4, S5 is declared so that we can you do the instantiation. Now when it comes to the begin, this is the instantiation, you say X1, X2 are the XOR gates, you can see it is nicely instantiated AB S1, S1 Cin, S sum, and the AND 2 is kind of reverse. So AB and S2, BC and S3, BC and S3, AC and S4 that is AND 2, and OR, the first OR is S2, S3, S5 that is this, and S4, S5 Cout that is this. Now we are going to say where this X1, X2, A1, A2, A3, O1, O2 is coming from. So we have, mind you, we have 2 XOR gate, 3 AND gates and 2 OR gates, okay. X1, S2, A1 to A3, O1 and O2, and that is specified before the begin. This binding of the component to the library package or the architecture is specified before the begin. So we go back and you see after the component declaration, signal declaration, we are specifying the configuration. So which say that for X1, X2 these are the instantiation kind of labels, colon that is a entity XOR 2 use entity work which is a work library dot XOR 2, that means that is the entity name. We assume that there was, we have written an entity called XOR 2 with multiple architecture which is compiled into work library, and you see in the bracket which is say XOR behave or beh, which is the architecture we have used, okay. So we assume XOR 2 has multiple architecture, this is a particular architecture we want to use for X1 and X2. So the syntax is for label the entity, use entity, library, if you have package dot entity, and within the bracket the architecture. Similarly, say for A3 and 2, use entity, library, here there is no package, it is directly compiled in the library, the entity, architecture, and you could even change the port mapping by kind of if you have used some other port names in the instantiation, you can change it from the formal to the actual whichever way you have used for the instantiation. So you can do the port mapping, and for all OR2, that means for all instantiation of OR2, use entity this particular library, entity and architecture. For others and do, that means here we have used only for A3, for all other and to use the particular library, entity, architecture, and the port map is done to change the port mapping. So that is how the specification, configuration specification is done, wherein the instantiated components are bind to particular library, packages, entity and architecture. Okay. So let us see the configuration declaration, so which has two purposes, which binds an entity to architecture. So we are assuming that this particular entity for which the configuration is written has multiple architectures, and which also bind the components which is used in the architecture to a particular library. So let us look at the very simple example wherein the entity is just bind to the architecture. So there this is the syntax, configuration, which is a keyword, a name. So here we are writing the configuration for full adder. So I have called it FA_con, FA_con of full adder is, and we say end that name, then that is the body of the configuration declaration, and inside we say for FA_str. So this is the architecture to which this particular entity is binded, okay, for FA_str N4. Okay. So very simple thing, we bind the entity to architecture. So this particular entity is bound to this particular architecture, but assume that you have a lot of components are declared and you want to bind those components to specific library. So that can be specified within this body of, like you say, for FA_str N4. Within this you can specify as we have specified in the configuration specification. So that is shown here, like configuration name of full adder is, and you say for FA_str N4, that is why it is, that is how the entity is binded to the architecture. Now within that you can say for A1, A2, A3 and to use entity, library, entity, architecture and so on. So all how we have done, like for others OR2 means for all OR2 we do not say anything, it can come from anywhere. But interestingly we say here for all XOR2, that means in our previous case you had X1, X2 to instantiation, we say use configuration work.xor2con. That means for this particular entity XOR2 there is an architecture, maybe multiple architecture. Also along with the entity there is a configuration called XOR2con, which binds the XOR2 entity to some architecture, which binds if at all some components is used within the XOR2, that is bind to a particular library. So that is how at the beginning we said that the configuration is hierarchical. So we have a configuration for the full adder and we also have a configuration for the component used within, and we just say use that particular configuration. So that is how the configuration declaration is done. So Now so the two things we have seen with the configuration is that basically configuration specification and configuration declaration. Configuration specification is specified in the architecture declaration region. So whenever you have some components instantiated in the architecture statement region, this configuration declaration specify where these component labels by labels you can specify where it comes from, which library, which package, which entity and which architecture, okay. And the configuration specification bind that particular entity to an architecture. Also it says if the components are instantiated where it comes from, and the configuration can be hierarchical. So you could write components with configuration and go to a top level entity where this components is used, and you can say at the top level entity to use that particular configuration for those components instantiated. So that is hierarchical. So that is kind of complete the library and packages. We have seen how to write generic library packages, how to put it in library, how to instantiate it, how to use generic packages, and how to specify where these components should come from by configuration specification, configuration declaration and so on. So we have a little more portion left in the VHDL for a logical conclusion before we start with the controller in digital kind of state machine. So maybe we will have a brief look at it and we will try to complete in the next lecture. So I just want to give various packages, operators and function so that you are familiar, you can use it properly. So we have seen this particular package already, like you have a package called standard logic 1164, which is an IEEE package in the IEEE library, and we know that the standard U logic is defined in that. We have seen it. It takes 9 values U, X, 0, 1, Z, W, LH and dash, which is don't care. And we have a subtype which is called standard logic, which is a resolved version of standard U logic, and I have briefly mentioned earlier resolved means when multiple standard U logic drives a bus, this resolution function tell what is the resultant value, that is the meaning of this resolved. We will see that as we go along in the VHDL, and we have a standard U logic vector defined as an unconstrained array, standard logic vector which is defined as a unconstrained array of standard logic, and we have in this standard logic 1164 package all the logical operators like AND, NAND, OR, NOR, XOR, XNOR and NOT overloaded for this particular standard logic and standard logic vector, okay. So you want to use that, then logical operators with this standard logic, then use particular library. And also it has another because this only specify the logic operators, but we need arithmetic operators, we need relational operators, but that is not found in the 1164 library package, and that is specified in this particular package like standard underscore logic underscore unsigned package, it is specified, and basically it specifies the standard logic and standard logic vector, and you have these operators, arithmetic operators, you have plus, minus, multiplication and division, you have relational operators like less than, greater than, equal to, not equal to, less than or equal to and not greater than or equal to. You have shift operators. Now mind you that this is called SHR, shift right, and SHL which is shift left, okay. And you can convert this many a times in the code. We need to convert a standard logic vector to an integer. Say example is that you have some address as a standard logic vector, and you are trying to write the VHDL code for a memory or a FIFO, and this the address location is an array. Okay, so you specify address as say 4 bit 1010. So it should go to the 10th location. So normally that is converted to an integer as a 10. So wherein this is used, which is called con underscore integer, and you specify the standard logic vector here, you get the integer it returns an integer which can be used as an integer type. So I think we will see in the next lecture all the packages, various operators, so that you can use these packages to quickly design. That's a basic idea. And also if you have a idea about various packages, various operators, it is very easy to code and very easy to be kind of keep compatibility. So what is the kind of recommendation of what is current packages, because there are some old packages which is kind of superseded by the new packages. So it is recommended that when you design, use the current packages than the old one and things like that. And some packages may be used for a particular only simulation, not for synthesis. So all that we will see in the next lecture. Please go through the portions, revise it, try to understand it, work out small example so that you become thorough with the syntax and you get the idea. So I wish you all the best and thank you.